Thursday, and I'm going to carry on with the lecture that we finished off on Tuesday. Okay, so we were doing acceleration on a point within a rigid body, and we're going to do one example on it. Then we're going into absolute motion analysis. Okay, so I'm going to just copy and paste what we have over here. So this is where we finished off last week. Okay, so just to quickly recap, so if a rigid body is under rotation, as you can see from here, and we pick a point P, now the acceleration has twofold, okay, or two components. One is the tangential, okay, which is alpha r, and the other one is the normal component of acceleration. So you do feel these two acceleration when you're in a car. How do you feel it? When you are going on a straight line, okay, when you're accelerating on a straight road, right? You can sense the tangential component. However, when you're making a turn, right, what do you feel? No, oh yeah, you feel you swing left and right, depending on how fast you go, okay? So that's where you have your omega squared r, okay? So we know the acceleration, right? So where we start off, where we finish off on Tuesday, we realize that our acceleration is equal to dv over dt, and then we know v is equal to omega r, okay? So we know that d omega over dt, right, cross r, okay, plus by omega dr by dt. So this is where we finish off on Tuesday. So I want to highlight that I'm going to note that d omega over dt, you can start copying now, okay, is equal to alpha, and dr over dt is equal to our velocity, right, which is equal to omega cross r. Okay, so now this is not times, this is cross. Okay, because later on we're going to use vector annotation. Okay, so the acceleration now will be equal, so we substitute d omega over dt, which is equal to alpha, so alpha cross r, okay, plus by omega cross r. Okay, I do miss out a cross over here. Okay, so this in turn has a equal to a tangential plus by a n. Okay, so a acceleration in magnitude can be determined by a is equal to a tangential plus by a normal. Okay, so important to take note that A tangential is in the same direction as, is usually in the same direction as the rotation, and AN is always pointing towards the center of rotation or instantaneous. Okay. So if I were to, I'll let you guys copy first. So if you look at this diagram, right? Okay, undo. Sorry about that. Yes. Yeah, I forgot my squid. Thank you so much. Thank you. You get a pint. So from here, what I mean by this statement over here, right? Over here, this is our rotational direction, right? So AT, okay, it's the same, usually the same direction as the rotation. More important is AN is always pointing towards, okay, the center of rotation or towards the instantaneous axis, okay. Right, so now we are going to do an example, right, which I have given to you on Tuesday. So on this example, which is this one over here, can you all get this question over here, please? Okay, I'll wait for you guys to finish copying first. Okay. Okay, so we're going to do this example over here. So at the instant shown, when they say the word at the instant, okay, so instant means, okay, the instant is a snapshot, or also at this moment only. So we're going to analyze this structure at this moment. Okay, the shaft and plate rotates with an angular velocity of omega 14 radians per second. Okay, so you can see omega is 14 radians per second, and the angular acceleration of alpha is equal to 7 radians per second squared. Determine the velocity and acceleration at point D. So this is the point of interest, right? Located at the corner of the plate at this instant. Express the result in Cartesian vector form. Okay. So in Cartesian vector form, right, we have our transformation. So this direction, All right. So X is our I, Y is our J, Z is our what? K. Okay. So that is the notation that we use. Okay. So we are given that omega, okay, given that omega is equal to positive 14, right? Why positive? Because this is omega over here is at what? Given the direction over here is going in the anti-clockwise, right? So omega k positive, as I said, right hand rule, right? And then it's going at 14k radians per second, and it's also rotating at alpha, okay? and alpha is at what? 7. Okay, so our alpha, hold on, let me check something first. No, this is not 14k. Okay, this is not 14. I'll tell you why it's not 14. My bad. This is 14 radians per second, and alpha is positive 7 radians per second squared. Why it is not 14 like what I thought it should be is because this axis, okay, the instantaneous axis that I'm going to draw in green, is tilted at an angle. Okay, it's tilted at an angle over here. And when it's rotating at this, I mean, when the instantaneous axis is at an angle, we have to find out omega. Later on, we have to find out omega in terms, okay, in terms of I, J, and K components. And also, in terms, later on, we also have to determine our alpha, again, in terms of I, J, and K components. Okay. So the first thing we have to do, right, we have to find, okay, we have to determine, in order to determine I and J and K components in both alpha and omega, okay. So we have to now determine the position of point A relative to O. Okay, so let me get this diagram, then you can see what we're trying to achieve down here. Okay. So why that is the case? Because we know that we have to relate our omega. We are later using omega position. So I'll call our position U, A to O, okay? And then we use alpha U A relative to point O, okay, to find the I, J, and K components for angular velocity and acceleration. Okay.